bring up our homework set number 5, and today's our final regular course day. Final regular course day today. We look at our chart here for the calendar. Only thing we've got today is the review, and then exam number 3 coming up Wednesday to Thursday. If you need an alternate date, just email me and we'll get something worked out. If you need something later or next week even, that's fine. Also had a few early takers, so that's completely at your availability. So let's take a look at our first problem here. And in this case, we're looking to exercise our Castigliano theorem. Sure, I got everybody okay. Let's see, microphone, real tech audio. Okay, should be good. You guys hearing okay out there in TV land?
Yes, sir.
Okay. So first problem here, we're going to take a Castigliano approach. We're looking at this crane rail on the back of LCS. We're launching a UUV out of it. We've got some weight load and some drag load, and it's working out at this 3-4-5 triangle angle here. We want to figure out what are the deflections, both the vertical deflection and the horizontal deflection of that beam using our Castigliano method. And then also check out what's the effect of having included or skipped that transverse shear portion. Sorry. So here's our properties. We're given everything for area and I. And here's our correction factor. For an I-beam, it works out to the area over the web area. So 2.2 is going to be our shear correction factor. Our load is at the angle there. So we're going to break it into 2 components. All right, we have a couple ways we could solve this. We could solve it all in terms of P, and then we get a diagonal deflection and break that into components. Or we can just say this P is a shear force and it's an axial force, and they're each of a fixed amount, 800 pounds in the shear and 600 in the axial, right? And then if we take derivatives in terms of those component forces, then we'll get the component deflections as well. It's a fairly simple setup. It's a cantilever beam. So if we just slice and say keep the free end, we're going to have M of X is just going to equal that shear force times X. Our F of X is going to be equal to that axial force. And then our shear force going to be equal to minus P sub Y, right? So we got M of X, V of X, and F of X. Only one of those varies with the position. So the other 2, we can skip to the shortcut and just going to say for the axial, P in the axial squared L over 2AE. For our shear, we're going to have correction factor, shear P squared L over 2AG. And then the one that we have to integrate, but it's only a single term, is going to be that shear times X, that's our moment, squared over 2EI. We do that from 0 to L, so we get the 1/6. That's our classic cantilever beam bending formula there, 1/6 P squared L over, or P squared L cubed over 6EI. And then we've got our axial turn there, and we've got our shear. So if we work out the axial deflection, it's going to come out right around a 1/10,000th of an inch with that load that we had of 600 pounds. For the shear deflection, we include the bending term. All right, so we're going to take that derivative. It's going to make it 1/3 PL cubed over EI. And then we see the squared on the shear is going to come down and take away the 1/2. So it's going to be correction factor times P times L over AG. And that one comes out to 0.35 inches. So just a little more than a 32nd of an inch of deflection on that beam. If we were to take the shear term off of there and just include the bending, I see I get 0.343. So if I put the no shear over the included shear, we're only missing about 2.5%. Less than 3% of the total deflection in this example is caused by the transverse shear energy, and most all of it's caused by that bending energy that we see right there. All right. And this beam, it's 12 inches high and 120 long. So we're kind of at the low end. We're at that 10-to-1 length to height ratio. And for longer beams, this error is going to get smaller and smaller because we know that the bending energy grows at L cubed and the shear energy only grows at a rate of L to the first. So the longer it gets, the smaller and smaller the shear term is. That's why we're often going to just omit that shear energy from the calculation. Anybody have any questions about that? All right, a couple things to remember. We can throw sign convention out the window for all our internal loads. So whichever way you want to draw V and M and F is fine, whatever's convenient. Also, wherever we want to draw X from is fine, as convenient. Might as well just put it from the free end here. But if we're working with the right half of a beam and we want to draw X from the right, that's fine too, because we're just finding a scalar value, the energy over the whole thing. All right, so that exercised our basic Castigliano here. We were able to work with the axial one, the bending one, and the shear out of those. Everything but the torsion in that problem. And we were able to use the shortcut member for constant load across X for the force and also for the shear energy. This is the only one we really have to be careful with when bending moment usually is not constant across the length of the beam. So we don't want to use this one unless we're sure M of X is a constant. But very often, axial force and torsion and shear are going to be a constant. All right, let's take a look at our second problem. Here we're looking at that same exhaust duct, but this time we've got a lateral misalignment. Before we had that angular misalignment with the torsion. Now we've got an offset between the decks where the cutout is of 1/4 of an inch. Right? So when we use our Castigliano method again, this time calculate what our reaction forces are at those decks. Right? We're going to neglect transfer shear energy. And note that because these decks are pretty rigid and they have all their own stiffeners and bulkheads, we're going to assume that they don't have any rotation to them. So although the hole was cut in the wrong place, it's still going to be level. Right? So what we do know for this one is that delta up here at the end is going to be equal to 1/4 inch. And then we also know that theta up here on the end, if we don't have any rotation, is going to be 0, right? Stays flat up here. So what I would normally take my Castigliano to find the deflection and or the rotation, we know those numbers, but we don't know what the loads are that go with it. And this is where we're going to apply our indeterminate version of the Castigliano method. So I take a slice of this one. I can keep the top or the bottom, either way. And I take a cut, and I know I'm going to have some reaction force. And I see I've got some curvature there, and I'm preventing it from rotating, so I should probably also have a reaction moment. Well, we're pushing it to the right, so that reaction force up there will have to be to the right. And I can kind of tell, because I'm smiley faced this way, that my moment is going to be curling like that. All right. If you guess the other way, you just get a negative number for the moment, or the force if you draw either of those the other. So it's okay to draw them whichever. I like to try to draw them so that I'll expect to get a positive number out of the reaction. Right? And the whole free body would tell me that whatever force I'm pushing with on the right has got to also be the same there on the bottom. And I've got anti-symmetry there. So however much curvature is at the top, I'm going to have the same curvature with the smiley going the other way at the bottom. So I'm also going to have a moment down there. And I just need to pick one end or the other. Once I find these two, I'll know what the bottom ones are as well. All right. So let's take a little slice from the top. I'll put X from the top as well for convenience. And I can see that if I sum moments equal to 0, say I've got M of X, I've also got M naught going counterclockwise, and then going clockwise, I've got P times some distance X. All right, if I sum moments right here where I made the cut. So M of X is going to be P times X minus M naught. You might have some other version of that if your reactions are drawn differently. And then my energy, 0 to L, and I have that FOIL term. So I've got to FOIL that out. I see I'm going to get one term with just M naught L, M naught squared L over 2EI. I've got the P squared L cubed over 6EI. that's the cantilever end type case for an end load. So we do see that one in there. And then I've got this term which combines the reaction force and the reaction moment in the same term right there. Since that came from the middle of the foils, we see it's got the minus. So there's two derivatives I can take. If I say I do the moment one first, du moment reaction equal to 0. And I cut left with these two terms. One for m naught, that's the first term, and then one from the middle of the foil term. So I can use this one. I have two unknowns, remember, P and M naught. I can use one of them to describe the loads between each other. And this one tells me M naught equals PL over 2. For a quick sanity check, I can go back there and I see that in the whole free body, P times L is going to be a clockwise moment, right? The whole body is going to get P times L. If I look at it from the top or the bottom, P times L clockwise. That's a force couple. And opposing that are both of my moment reactions. So I take that PL and cut it in half, and that's M naught. So that checks out okay. That'll make everything balanced. But we still don't know a number for either one. So we go back and we can substitute for M naught, solve for P. So my other choice is du dP equal to displacement delta. That's my 1/4 of an inch, right? So I can take this derivative with you. I get PL cubed over 3EI. There's the end load part, and ML squared over 2EI. That comes from the foil term in the middle. So I've got those two equal to delta. And then I can sub in PL over 2 in here for M naught. Right. So it looks like I've got PL cubed over 3EI, and then this coming in right here. I got the PL over 2 goes in for my moment there. So I've got a third minus a fourth. That gives me 1/12 left. And then we already know delta. We don't know P, so we just rearrange it. 12EI delta over L cubed. Works out to 8,700 pounds. And then my moment is going to work out just about 1,000,000 inch-pounds. Now, those are pretty large numbers. Remember that with a 1/4 inch of misalignment, what we're going to probably end up trying to do is we'll get some bolts in the misaligned area and then through the anchor, like we saw on last week's class, and then we'll start to tighten those bolts down, and they'll straighten up and they'll do the moving over. So we're not going to have to get a giant torque wrench and put 1,000,000 inch-pounds on there or push over with 8,700 pounds. This will be slowly applied by tightening down all those bolts. It'll slide it over that tolerance that we need. But we see once it's on there, it's carrying an awful lot of load, which is going to translate to some big internal stresses as well. So with our indeterminate Castigliano, we still have the same rules. du d force equals displacement, d energy d moment equals rotation. Only this time, instead of being after the displacements and rotations, we use known values, those, and get our loads, the reactions that we don't. Anybody have any questions about that? All righty, let's jump to our third problem. And here we're practicing again Castigliano, but we just want to look on a multi-component structure. This is not unlike what we did in class with the L-shaped bar. We pass some loads around, we calculate the energies, and we just add them up. It's all a summation. We're going to neglect transfer shear effects. We'll put all the loads on our free bodies. So if we look at the structures, we've got that diagonal beam with a center support, load on one end, and another support on the other end. They're all pin supports, so just force reactions, and that's it. And then we have that axial bar propping up our middle of the beam. So if I draw the bar first, and I just say, okay, for any axial bar, F is going to be the axial force. If I draw it positive tensile, it's going to look like that. If I draw it like this, then I pass it off just like that to the center of the beam. All right, so however I draw it on the bar, it's equal and opposite on the beam, just like we pass stuff between beam number 1 and 2 in the in-class example. And then I need to figure out what some of these loads are. Well, if I sum up moments about the bottom, I see P is all the way over here, and halfway over here is my reaction force from the bar. So I can see that F1's minus 2P. That means it's going to be pushing up with 2P. That makes sense. It's up 2P. It goes clockwise. P times double the moment arm going counterclockwise. So that zeroes out the moment at the bottom. So I've got 2P up in the middle, P down on the right, and also, or P down on the left. And that means I'm also going to have P down on the right. I can get that from summation of forces in the vertical. Now, once I know F1 is minus 2P, I also now have the compressive load that's carried in the bar. And then we just need the energy for each one of these members. For the bar, it's pretty simple. We got a constant axial force, so F squared times the length of the bar. Because of our triangle shape here and L on the diagonal, this is 3/5 of L, so we put that in for length, and over 2AE. Plug and chug a little bit there, and we get 6/5 E squared L over A. Then I've got two parts to that beam. I could slice it somewhere here. I might as well keep this in. I could slice it somewhere down here. I might as well keep this in to minimize the number of loads. So if we look at the top one, I've got 3/5 of P running into the bar and 4/5 going perpendicular to it. Remember, the total load on that end is just P, that's my hypotenuse, and I break it into an axial and a shear part. So my moment that's carried along there is going to be the load 4/5 of P times X. And then my axial is just going to be minus 0.6 P. That's a constant all the way through. So F squared L over 2AE for the axial, and then integral M squared over 2EI. It's just a single term. We square it, comes out to a cubic. And then here's our values. Now the 4/5 in there carries out, it gets squared, and there's a half down there. 3/5 is squared and 2. So this is what we end up with for our energy. We get an axial term and a bending term. Now, when we look at the bottom portion of the beam, there's the exact same load as on it, P right here. Still going to be 0.8 P going transverse. 0.6 P is going to be going tension instead of compression, but it's still the same magnitude. And our energy really doesn't care whether the sign is positive or negative because we're going to square it. So F squared L over 2AE, and the same expression for M3 of X as M2 of X if I just conveniently put X down from the bottom for this piece. All right, remember I can rearrange X for each energy that we calculate. So I'm going to get the same value for you, same bending energy, same axial energy. Add them all up. The UDP is going to be PUDP for piece 1, piece 2, and piece 3. That gives us our total deflection right there. And if we plug and chug our way on down, the bending term ends up 32 over 75 or some decimal equivalent, and axial ends up 78 over 25 if you bother to do the common denominator. But we can see we've got a term that contributes from the bending, and that one has the L cubed on it, so it will be a pretty hefty chunk. And then we've also got this term here from the axial energy. That's the compression that's going in all three. Remember, compression and or expansion all helps to move that beam along. If we think about what this looks like from back here, I know I've got some compression here and some, it probably goes something like this for that beam, and the bar got shorter in the process, right? So we're coming down here some when this axial bar shrinks. There's also some bending energy that's adding to this displacement out here. And all those movements get combined, and we don't have to think about them. We're trying to calculate out how much rotation do I have, plus how much distortion, all that. As long as we did the energy in here, it all counts up and gives us a deflection. So there's our multi-part Castigliano in action. Any questions about that? All right, let's take a look at a Rayleigh-Ritz problem. Here, we're going to look at a cargo pallet resting simply supported, and we've got cargo evenly distributed on the right-hand side of the pallet. Want to use a one-term Ritz approximation to determine what's the deflection of the beam at the center point. And then we're going to compare that with a dummy load method, which is quote unquote exact, but will take us a lot more work. We want to see how close can we get by going the quick way. All right, pushing the Staples Easy button. See how accurate can we be with that. We're going to use a single term Ritz approximation. So we know that's just going to give us a simple symmetric deflection shape. All right, something like this. Now, instinct would tell us that if the load's over here, what we're probably going to get is something a little bit more like this, with the load further to the right. But how close those red and green lines get in the middle is what these two methods will tell us. We don't need to do any reinventing of the wheel. We can flip over here to our potential energy formulation. We're going to have bending energy, so we just need to take that EI over 2 times curvature squared and integrate that. And then whatever external loads we have. In this case, we just have a distributed force. Distributed force times dx, so a little force per length times a little slice of length. Those two together give me my differential force, and then force times the displacement gets me a work. So we're just going to be exercising this term in our specific case right here. And we got a simply supported beam with one term. So here's my V, here's my V prime, and here's my V double prime. I don't need to spend any extra time trying to remember what sine, the cosine, the sine derivatives are. We've got them right here, and we just the junk comes out in front. Also of note, for the energy terms, sine squared or cosine squared with these setups gets us L over 2. So the energy term will usually, the bending energy will usually reduce to one of these two. Right here. So here's our setup. Energy, just a single term. We got A pi squared over L squared sine, and that's our second derivative. We're squaring it, so everything goes away positive. What we're going to be left with in there is just a sine squared. All these other constants we can pull out. So that sine squared from 0 to L will just work out at an L over 2. That'll take away from the 1 over L to the 4th, so we end up with an L cubed out there. And then the over 2 will also hit out with the 1/2 and get the slip. So a real quick integration there. Then here I'm L over 2 to L on my sine term. That works out to be L over pi. If I integrate sine, I go up to minus cosine, and then I'm still just plugging in here and here. One of them 0, the other's 1. And we get L over pi, and then these two constants come. So there's my two terms. The whole idea is that we're not going to get an exact answer, but we want to make this difference between the internal energy and the external work as small as we can. So this cap pi function goes something like this, with pi having some values. And then we have any number of A axes. 1 or 2 we can draw. If we had an A1 and A2, we'd be looking at a 3D saddle point. We just have one A to solve for. So we're looking for what value of A do we get the smallest amount of this error right in here? Where is this height of pi the smallest? When do U and W get close together? That's going to be the saddle point. That's where the derivative of that potential energy is 0. All right, so we take that derivative and then we just solve for A. We see it comes out in decimal form, 2 over pi to the 5th. That works out, as we all know, 0.00653 and some change. So there's our deflection, and it's got some constants out behind it, but here's our number that goes in front of those. And displacement at V of L over 2 is just going to make the sine term go to 1. So we just get A as the displacement at the middle. So there's my Ritz approximation. Pretty quick and easy, 4 or 5 lines, maybe 6 at most. Now the dummy load method, we're supposed to get a little better accuracy, but we're going to have to put a force on at the center. We don't have one of those. And then we're going to have to take at least 2 slices, one through the left side and one through the right side. So left side's not too bad. I've got a reaction on the end. It is 2 pieces, but it's a constant, or 2 terms, but it's just a constant. And then times X gets me my moment. On the right-hand side, you can, if you want, put X from the right. I kept it from the left just to be consistent and have a 0 to L over 2 and then another one over 2. But you can, if you want, draw X this way and they both be 0 to L over 2. That's okay. Save you a little bit of algebra. But now we've got an M squared for this side. We've got a much messier M squared with at least 2 terms here, and those 2 terms have to get FOILed as well. So after we do all that number crunching, we come up with all these different fractions. A lot of chances to have a little mistake along the way, but if maybe we let the computer do the integration for us, come up here, 5 over 768 comes out 00651. Right? Down to the 3rd decimal place, we're here at 653 with the Ritz approximation. Same coefficients outlined. So as long as we're picking a decent shape, and obviously a sinusoidal shape is good for a simply supported beam, we can see that those come really, really close together for much, much less work than we'd have to do with the dummy load method. Or integrating up to get displacement if we went the conventional beam bending where we integrate up. We'd have to integrate 2 functions, a V1 of X and a V2 of X, and that's also a lot of work. So Ritz approximation, if we're only after a value that's pretty good, then this works out pretty nicely for us. It turns out those red and green lines were really close together out there. Do anybody have any questions about this Rayleigh-Ritz method? All right, let's take a look at number 5. Here we're working with a lug wrench on this access hatch. Bonus points if you realize we're never going to get that hatch off unless it's a left-hand thread because we're tightening it. I never got around to reversing this photo, but or drawing. We've got a beam that's active right here and another beam right here. These 2 over here aren't carrying any load, so we don't have to worry about them. But this is what our typical lug wrench looks like. We've got a load on the end there we're pulling down on. We want to know what's the deflection, but also the rotation at that spot. So we're going to need to throw a dummy moment on there in order to get that rotation. No transfer shear effects, but this is a full 3D problem, so we're going to need to pass the load along. All right, for the first beam, we'll just draw X from the end. We could take a slice anywhere we'd like. Over here, I just cut it from the end. Usually minimal amount of mess if we take it from the end there. So we're going to put P on there and then a dummy moment. I called it M0, call it whatever you like. We need an M of X. And then we do need to keep the shear on there, but we don't have to make an energy. All right. So V is just going to equal that shear force P. And then M1, if I draw it that way, it's going to be M0 plus P times X. So we've got a FOIL term for our bending energy. We chug that along and we get these 3 terms right. Now, if I go to the end of beam number 1, M at L, so the moment right where it connects to beam number 2 is M0 plus P times L, and it's going this way. If I plug in at L, this is what I get. And my shear force over here is still just P. So I know what the loads are at this intersection right here. This is what I've got at the end of beam number 1. The exact same loads, but going in the other direction, transfer to beam number 2. So I could take a little slice and keep right here, or I could figure out the reactions and keep the root end of the beam. Either one is fine. Whichever one you're more comfortable with is what you ought to do. I transferred the load since we already did the work to get V and M on the first one, we can just flip them and put them on. And I see the axis that was bending on beam number 1 is actually a torsional axis because we made a right turn on beam number 2. So I'm going to have a T of X, a torque in beam number 2, M naught plus PL, and that is a constant, so we can use the short formula. And then M2 of X, we still have that shear force hanging around, so I'm also going to get a cantilever type energy on this. So P times X or M2 of X. You might get a plus or minus of these. It doesn't matter which way you drew them because they're all going to get squared. So we just plug and chug on there. This one comes out with a single term. It's our cantilever end load term. And then this one gets foiled. So we have 3 terms with the shear energy. I add up U1 and U2 together. And then my total energy between both of those, du dp, is going to give me my deflection delta. If I plug and chug along there, here's the terms that get left over. I see 2 terms with P and then 2 terms with M naught. Remember, that was a dummy load. So now that we're all the way down, we can cross that off. And then I take du dm naught, which is why we have to have M naught in there, is to get this rotation thing. Again, I get 2 P terms, 2 M naught terms, and it's only after I take that derivative, because otherwise I couldn't take it, then I go back and cross off the M naught. So I've got these 2 surviving terms for delta, comes out 3.7 inches, and I got these 2 surviving terms for theta. We're going to get a decimal number like this. Remember, this is in radian. It'll cancel out all the units. So we can always convert to degrees if we want a more satisfying number, about 16 degrees on the end of the range. Anybody have any questions about that? That's about as complicated as we're going to get in here. It's a 3D load transfer, so we got bending on one, creating torsion on the other. I'd expect you'd probably see more 2D type stuff if I were betting on exam part, but this gives us a practice in some 3D. All right, for number 6, we're looking at expansion joint in that same exhaust duct. And it's been installed here. The idea is that instead of being wedged between 2 rigid decks, and we saw in class how much force and stress builds up when we have 2 fixed ends and thermal expansion, we put a spring in there. All right, it's a fairly beefy spring, takes 700 pounds to move it 1 inch. And it's made out of sheet metal, very similar to the duct itself, but it's still flexible, right? Much more flexible than a rigid end, and that can drive our load way down. So we got our properties for the duct, modulus, our area, and our coefficient of thermal expansion. And then we're going to assume our temperature, delta T, is 800 down here, and then 2 decks up. When we get to the top of this one, it's going to be down to 600. We have an insulated exhaust duct like we saw last week, but a little bit of that heat is still going to make its way out. And while it's doing that, the duct wall cools a little bit, so we got this taper delta T of X. Starting at the bottom and gets a little bit cooler as it goes out. Right? So we can treat this like a 2-bar type mechanism. They just happen to be end to end instead of parallel, but a spring, whether it's up there or beside it, it's still going to behave the same. So we'll say, to make the displacement the same, we know U for the bar is positive. We'll say that U pushes into the spring. That's fine. So force on the spring will also push up or be a compressive load on that spring. So F spring equals K times U. That means my expression for the displacement of this node right here, I can just say is F for spring, F of the spring over K. Right? So set it up like that. And then I have my usual thermal Hooke's law right here for my bar. We can grab that one right there with that load pointing out. And that's everything that I need to set up this problem. Works just the same as any other 2-bar with bars side by side or end. F bar equals minus F spring. The way I have them drawn, if I'm pushing in on the spring is positive, the spring pushes back on the bar, and there's F bar. So F bar equals minus F spring, just like we did for any other one. And we've got an expression for U in the spring, and here's our bar. U bar equals U spring. They have to move together. And then we're just going to make a substitution, sub in for this F sub spring, put in minus F bar there, and we can solve for the force in the bar. Works out to 634 pounds compressing on the bar. That makes sense. And then the spring, 634 pounds, the way we drew it, it's going to be pushing in on the springs. So both are receiving some compression there, which is what we'd expect the way this is set up. But no, we were getting up into the thousands of pounds for other combinations where we had reduced to no displacement. There with the spring, even though it's a stiff spring at 700 pounds per inch, it still greatly reduces the force. Stress is going to be way down, only 44 psi. We were way up into the thousands of psi for those fixed end cases we looked at in class. And then for the displacement, well, you could go back and do this one and get 0.907, or you could also just put F over K for the spring and also get 907 a little bit faster, but they should match up. Did anybody have any questions about this one here? A little bit different look for our brain to put them end to end, but this is behaving the same way as if we had a spring and a bar next to each other. Same kind of setup. They both move the same distance, equal and opposite forces. So whether they're side to side, like we did in the in-class example, or end to end, there's still two bars with a shared displacement. All right, let's look at another two bar, this one side by side. We take the wing off this Harrier, and in the morning, first light, it's 70 degrees in the hangar. Everything's 70 degrees, both the cart and our wing. Then we roll it outside. We go to Smithfield's to get some lunch. We get our vinegar barbecue and hush puppies and all that stuff. And then we come back, and the sun in the afternoon has heated up the wing to 130 degrees. Meanwhile, it's providing shade for the scaffold that's underneath. So that only got up to the muggy ambient air temperature of 100 degrees. So we got different delta T's, and then also different materials. The wing's aluminum and the scaffold is steel. So we want to see what sort of loads and stresses do we generate in this combination right here. So my delta T for the steel is going to be 30 degrees. Delta T for the aluminum is going to be 60. And then we got all the base properties right there. All right. Again, we're dealing with a two bar, so U aluminum equals U steel, forces equal and opposite, and we have a constant delta T. So it's just going to be two easy plug and chug terms. And we just need to make a substitution, either plug in for the aluminum or the steel force to get down to one unknown. If I plug in for steel, I see I get the alpha delta T for the aluminum on the positive and alpha delta T for the steel on the negative. We've got more delta T and more alpha, so this should definitely come out positive. And we see it does, comes out with 18,000 pounds right there. And then the aluminum, same force, but it's going to get compressed, right? If we do our quick sanity check, the aluminum got heated up more and has a higher expansion, so it wanted to go way out here. The steel got heated up a little bit, but it also had a lower alpha number, so maybe it only wanted to go to right here. And in order for them to be stuck together with those big retaining pins, one of them over here and one of them over here, I'm going to have to push back on the aluminum to get it over there. I'm going to have to stretch the steel out for them to be in the same place. So I should definitely get tension on the steel, compression on the aluminum. That makes sense. Force per area gets me my stresses. I see I've built up 7,000 psi in the steel and 3,600 in the aluminum. And then either one of those is about the same amount of work. Comes out at right around a 32nd of an inch of deflection. 031 would be a 32nd. We got 030. So another angle of a two bar, different materials and different delta T for this one. We've got that one covered right here, 2-ball parallel setup, no external load. So F1 plus F2 to 0. And then displacement 1 equal displacement 2. All right, let's look at our last problem. We're looking at a thermal load applied to a ship deck. So we've got our engine nozzle up here. It tapers out a bit like this, coming down. And then we get a pool of exhaust like this with the hottest spot in the center and then kind of tapering out in contour circles till we get to the edge. We're going to say it's 1 panel wide exactly. So above the ambient deck temperature, we heat up the middle the most. That's this T0 value. And then it tapers down. In order to get it to go up and back down, I had to make it quadratic, but it's just a little bit of algebra. From 0 delta T to 0 delta T on our ends and max delta T in the middle. So here's our delta T of X function. And we talked about these T's. They're really good against bending. They're not great in torsion. So we're going to treat them as restraining the displacement here, but allowing rotation. So the deck's going to pop something like that, a sinusoidal shape. I've got my length, I've got the thickness, and I've also got the width out of the page of the panel. So we can get our I value nice and easy. It's just a rectangle for this section. So my delta T is a delta T of X function. All right. And I want to figure out how much delta T, that delta T naught, will it take to cause my beam to buckle. Okay. So we got a pin-pin type connection with those T's. They allow rotation pretty easily. So L effective is going to be L. P critical, I don't have to do anything thermal to figure that out. Just the material and the geometry. P critical comes out 925,000 pounds. All right. Pretty beefy deck to cause the buckle. And I know that with an axial bar, we set up F to be positive tensile. So my F is going to equal minus P critical at the point we get it to buckle. Here's my expression for displacement, FL over AE plus alpha integral delta T. And we're going to say that those stiffeners can rotate, but they don't move. We've got lots of beefy flight deck around it. So we're going to say the displacement across holds at 0. So I got the mechanical displacement here, the thermal displacement here, and those have got to balance out. We put in minus P critical for our force because it's compressive. We know only compression can trigger buckling. We could try really hard, but it's difficult to buckle something in tension. So we work through here, and here's my expression for delta T naught. I plug in a minus P critical for F there. We see that's going to turn it positive, and the delta T that it takes to buckle then is 128 degrees. That's going to be this delta T at the center and then some tapering load out there. So it doesn't take a whole lot of delta T to cause this elastic buckling phenomenon with these dimensions for the deck. Now, right at the onset, when it's about to buckle, I can see that my axial stress is going to be pretty high. 925,000 pounds is a lot of force, even for a thick steel plate. We see that comes out at 15 KSI. So maybe, depending on your deck material, that could be a third of yield or a fifth of the way toward yield. But it's a significant number when anytime you get up into the tens of thousands of PSI. And compressive. All right, anybody have any questions about that? We got to practice a delta T of X that was variable. And then in this case, we had U equals 0. All right. If we had non-zero displacement, say 2 bars together, and we want to see when one of them buckles, no problem. This formula is still good. We just set U1 equal to U2 instead of U equal to 0. Right. So the mechanical part, the thermal part, that's the same in all these different problems we're looking at. We just decide what's our condition. This one, we said there's going to be no expansion. If we were looking at how long it would take maybe for that wing to buckle, how hot would we have to buckle, get that wing to be to buckle in problem number 7, we could have U1 equal U2. And then we would know the force is minus P critical in the aluminum one, and we solve for the delta T. So same formula, we just figure out what we want to set U equal to. 0 here. If it's a 2 bar, we set U1 equal U2 or so. Did anybody have any other questions on this thermal or energy materials that we've gone over? All right, so again, this is our last regular course day. Apologies that the recording thing did not work out on Teams, so I don't have a way to post that one, but I'm glad that folks were here and able to tune in on that one. So thank you for coming in and watching that one. We've only got the exam coming up, and you can take that one to go, or you can work it in class. Either way, I'll be around to answer questions that you might have, but I will post it with full instructions like the other ones. Otherwise, thanks for coming in and taking the class. I see mostly repeat offenders here, so thanks for taking multiple classes with me. And don't forget to do your course eval forms on the Python there. If anybody out on TV land has not done one of those before, just email me and I'll walk you through where to find those eval forms. But they're on your Python login page. Unfortunately, I can't show it to you because I don't have the same screen that you do. But it's just 1 to 5 ratings and then comment blocks and things like that. But we'd like to hear back about the course and how you liked it. So we'll see some of you folks on Wednesday, and otherwise, again, appreciate you having all in the class.
Thank you.
We're teaching next quarter.
Yeah, I've got structural dynamics FEA, which is 4522, and not applicable for you guys, but the 2000 fluids kit. That one goes every other. I don't know if you'll get the credit, but it would fill in a block in your matrix, I suppose.
Final quarter, there's a lot.